Example 3. The value of a certain investment grows according to the following rule. Next year's balance equals 1.07 times the current balance. A. Find the percentage increase each year and explain why the balance is an exponential function of time. As we did with linear functions, let's begin by filling out a table. First, we will need to ID the table. That means determine the independent and the dependent variables. We are told that balance is a function of time. That means balance depends on time. So balance, the variable we really care about, is our dependent variable. And time is the variable that the balance depends on. It is our independent variable. We will put our independent variable, time, in years, on the left side of the table, and our dependent variable, balance, in dollars, on the right side of the table. We are not told what we have initially, at least not yet, so we won't be able to complete the right side of the table, but we can show how the function value, or the independent variable value, is increasing. We have next year's balance equals 1.07 times the current balance. So each function value in the chart should be multiplied by 1.07 in order to get to the next function value. Since this is the best we can do as far as completing our table goes, let's go on and answer the question. Find the percentage increase each year and explain why the balance is an exponential function of time. Once again, we were given next year's balance equals 1.07 times the current balance. 1.07 is a decimal. To turn it into a percent, we multiply it by 100. That means moving the decimal to the right 2 times. So instead of 1.07, we have 107%. Moreover, instead of multiplying by current balance, we can change the multiplication sign into the word of. This gives us next year's balance equals 107% of the current balance. Notice 107% is not the percent increase. It is simply how next year's balance compares to the current balance. We could split up 107% into 100%, the part of next year's balance that is the same as the current balance, and 7%, the part of next year's balance that is greater than the current balance. We could also write the balance increased by 7%. That is, next year's balance is 7% more than the current balance. This is the percent increase. Recall, a function that changes at a constant percentage rate is called an exponential function. The balance of our function is increasing by 7% each year. This means balance is an exponential function of time because it grows by a constant percent increase of 7%. Part B. Assume that the original investment is $800. Find an exponential formula that gives the balance in terms of time. Now that we know the initial value is $800, we can complete the table above. $800 corresponds to year 0. To get the balance that corresponds to year 1, we multiply $800 by 1.07. The result is $856. Now we can multiply the current balance by 1.07 again to get to next year's balance. We get $915.92. To find a formula for the balance after t years, let's review the general formula for an exponential function. The general formula for an exponential function is n equals the initial value times the base to the t, where the base is the number you multiply the current value of the dependent variable by in order to find the next value of the dependent variable. Note that the t here simply represents the independent variable. We use a t because with exponential functions, the independent variable is often time. The n represents the dependent variable. In our example, the initial value is equal to $800, and the base is equal to 1.07, since that's what we multiplied the current value of the dependent variable by to get to the next value of the dependent variable. So our formula is 800 times 1.07 to the t. And since this gives the balance after t years, and balance is in dollars, the unit here is dollars. Part C. What is the balance after 10 years, 40 years, and 50 years? To find each of these balances, we will use the formula above with these values substituted in for t. The balance after 10 years is 800 times 1.07 to the 10. Using my calculator, I get that this is approximately $1,573.72. The balance after 40 years is 800 times 1.07 to the 40th, which is approximately $11,979.57. Finally, the balance after 50 years is 800 times 1.07 to the 50th power, which is approximately $23,565.62. When you perform these calculations, be sure to use order of operations. 1.07 should be raised to the t power before multiplying by 800. Also, it is appropriate to round to the nearest penny since we are working with money. Part D. What is the change in balance over the first 10 years? Compare this with the growth from year 40 to year 50. How is this reflected in the shape of the graph of the function? The change in the balance over the first 10 years is $1,573.72 minus $800, the initial value. Thus, the difference is $773.72. To find the growth from year 40 to year 50, we will subtract the balance after 40 years from the balance after 50 years. That is $23,565.62 minus $11,979.57. This equals $11,586.05. The growth from year 40 to year 50 is almost 15 times the growth over the first 10 years. This dramatic difference in growth can be seen in the shape of the graph of the function. Notice the graph is increasing at an increasing rate. That is, the rate of growth is slow to begin with, but escalates as we move to the right. In practical terms, this means the longer you have money in this account, the faster the money will grow.